All right, we are working on the review sheet, the practice problem sheet I gave out in class Thursday and Friday. If you have some other teacher, you might have not have given it out in class, but you should be able to find it on Blackboard if nothing else. So let's start with number 1, where we have Santa Claus out delivering Christmas presents, running low on reindeer food. Hanukkah-Harry is flying over Santa Claus to do some mid-air refueling, where he drops a bale of hay onto Santa, so Santa can feed his reindeer. So, situation: Santa is cruising horizontally at a constant speed of 40 meters per second. So, I'm just going to skip the art and do Santa cruising horizontally at, actually, let me, 40 meters per second. And then Hanukkah-Harry is above him, moving at 70 meters per second, also horizontally, going in the same direction. And whoops, there we go. All right, so here's Harry, 70 meters per second. He's also going horizontally. And the altitude difference between them, there we go, is 45 meters. And so we want to know how far behind Santa Harry should be. So I'll call that, we'll get to it in a minute. We want to find how far behind Santa in meters Harry should be when he drops the package in order for it to land right on Santa. So the thing to understand here is this is a relative motion problem. You got two objects moving both horizontally at different speeds, and you can set up this up in a number of different ways. You can actually do it sort of straight away. You can do something where you have, like, say Harry drops the package, figure out how long it takes the package to get to Santa's height, and then say Harry goes, figure out how far the package goes this way. So what happens is Harry is flying along, Santa's flying like that, and Harry drops the package, and it keeps Harry's horizontal velocity, but then it starts, curving down like that, as it gets accelerated downward by gravity. So one way is to just sort of do that and then calculate how far Santa goes in that same period of time, and then figure out how far behind, sort of backtrack to get the distance. I think it's much easier if you do it in either a reference frame attached to Harry or one attached to Santa. So let me do this in the frame attached to Harry, and I'll show you how that works. Or sorry, a frame attached to Santa. I'm sorry, let me do it in a frame attached to Santa. So in the frame attached to Santa, Santa's standing still, right? And Harry cruises by 45 meters above at some speed, still going horizontally, right? So this is like from Santa's point of view. The ground is moving past underneath Santa, and so Harry is coming up from behind him. So Harry has some speed relative to Santa. So we'll call this VHS, which is velocity of Harry with respect to Santa. This up here, the 70 meters per second, I'm going to say there's a ground down here that's stationary, so this is velocity of Harry with respect to the ground. And this here for Santa is velocity of Santa with respect to the ground. So we're using the old Giancoli notation system, where VHG is velocity of Harry with respect to the ground, SG means Santa with respect to the ground, HS means Harry with respect to Santa. Okay, so what we can do here is we can because of this Giancoli thing, because of this notation system that Giancoli gave us, we can set up an equation relating these three. And the rule is we set it up so that the subscripts that are close to each other match, and those are the two things you're adding. So here we can make a match out of the S here and the S here. So we do velocity of Harry with respect to Santa plus velocity of Santa with respect to the ground, and that's going to equal the velocity of Harry with respect to the ground. So you take the outer ones. It's like you're taking these two and smushing them together, and the S's annihilate each other. This is velocity of Harry with respect to the ground. And we know from before, let me just switch colors so I can sort of keep things colorful and lively. We know before that this is 70 meters per second. We know that the velocity of Harry with respect to Santa, well, that's what we're trying to find. So VHS, and then velocity of Santa with respect to the ground is 40. And then it's not hard to see that velocity of Harry with respect to Santa equals 30 meters per second. So velocity of Harry with respect to Santa, 30 meters per second. Santa's standing still in Santa's reference frame. I mean, anybody in their own reference frame is stationary. It's like your head doesn't move in your reference frame, right? Because it's always the way you're looking and where you are. So, so Harry's cruising over at 30 meters per second, and he drops this package onto Santa, who's standing still in Santa's reference frame. Now it becomes a little easier because now you have this package that starts, some distance d away. So we'll call that d, and it starts off, v naught for the package is Harry's velocity with respect to Santa in the I direction. We can do this in vectors or not. I'm going to do this with vectors. So it's going this way initially, and then it sort of curves down. It doesn't accelerate horizontally because there's no gravity, none of that. So the acceleration of the package is just going to be negative g times j hat. So let me show you, let's change colors again, and let me show you the coordinate frame I'm using here. It's the usual, but I just want to make sure we know y and x. And this is attached to Santa, so these don't move with respect to Santa. Okay, so how far down does the package have to travel? This is 45 meters, and that's the answer. The package has to go down 45 meters. So delta y is 45 meters, but y, positive y goes up. The package is going down 45 meters. So delta y has to be negative 45 meters, and that's going to equal the initial velocity in y times t plus 1/2 acceleration in y times t squared. Well, acceleration in y is negative g, right? This is our y component of acceleration here, what gets multiplied by j. And initial velocity in y is 0. Initially, the package is just going horizontally, so Harry sort of does this bombs away thing. It starts falling, but, so let's switch to purple now. This term is 0. Because the initial y velocity is 0, so this is really just ay is negative g, so we go with 1/2 g t squared, and that equals negative 45 meters. So I said on the worksheet you can use g equals 10 meters per second squared, and that makes it much easier because then it's negative 45 equals negative 1/2 times 10 times t squared. So you bring the 2 over, this becomes negative 90, bringing the negative over, it becomes 90, and then bring the 10 over underneath, it becomes 9, which gives 9 equals t squared, and therefore t equals 3 seconds. So that's how long it takes the package to fall. Now, Harry, how far does the package move horizontally? That's even easier. We want the package to move d horizontally, and that's going to equal the package's horizontal velocity in x, which is constant. Okay, so remember the package is not accelerating horizontally, so its velocity in x is just constant. And in fact that equals, well, times the time it takes to fall. So the time it takes to fall this far is how long the package has to move horizontally from Harry to Santa. Vx, this x component of velocity, is just the x component of the package's velocity, which is just Harry's initial velocity. So this equals velocity of Harry with respect to Santa times time, and that equals, so velocity of Harry with respect to Santa was 30 meters per second. Let's scroll down just a teeny tiny bit here, there we go, and boom, boom, times 3 seconds equals 90 meters, and that was this thing d. So that's your answer, 90 meters. If you used 9.8 for g, you'll get something slightly different, like 90.9 or something, but whatever, it's the same. So one more thing to think about. So what this says is Harry should drop his package when he's 90 meters behind Santa horizontally, and that'll cause the package to fall in this nice little parabolic arc that will end up smacking, right down on Santa's sleigh. One nice thing about that is that, or one interesting thing to note about that is that if it's 90 meters back, it takes 3 seconds to fall. By that time, Harry will have moved up 90 meters. So when the package hits Santa, I'll draw that in like this pastel blue. So when the package is here, Harry is right up here, directly above. And so what actually happens is as Harry moves forward, the package just falls and stays directly under Harry. So that's kind of an interesting thing. And if we'd done this from Harry's point of view, it would be a problem or from a reference frame attached to Harry, I'm just going to sketch this quickly, it would be a problem where Harry is standing here still. Santa is actually moving backwards towards Harry. So the velocity of Santa with respect to Harry is negative 30 meters per second. This is our y and our x, which are attached to Harry. And then Harry's just dropping this, so he's basically just trying to time his drop so that Santa is underneath. It's the same problem. It's exactly the same situation. It's just from Harry's point of view, where Santa's going by underneath him this way, instead of Santa's point of view, where Harry's going by this way on top. So that's problem